In 4.3, we are now going to be able to use what we learned in 4.2 as a direct application of what you learned in 4.2. In 4.2, you learned two things, angle bisectors and perpendicular bisectors. Well, what can those do in a triangle? That's what we're going to learn about here in 4.3. 4.3, we're going to learn this thing called a circumcenter. A circumcenter is created by the intersection of all three perpendicular bisectors. All three perpendicular bisectors are concurrent. They actually intersect at the same point. This point P right here in this example. The circumcenter has a special property about it, and it is one of four things you're going to have to distinguish from each other. We're going to learn four things that are all made by concurrent lines. This line here, and this line here, and this line here are all made from perpendicular bisectors. It creates something called the circumcenter. Later, you're going to learn that concurrent lines also can be made by angle bisectors. And when you have angle bisectors, it creates a place called the incenter. There are two more that we're going to learn. One's called the centroid, the other one's called the orthocenter. Those are coming up in future sections. So keep in mind, you are going to have to know the differences between them. And the biggest difference right off the bat for a circumcenter, it is created by perpendicular bisectors. I have to know that this is perpendicular and goes through the midpoint. This is perpendicular and goes through the midpoint, two congruent pieces. Two congruent pieces goes through the midpoint and perpendicular. All these three lines intersect at this point, and point P is the circumcenter. Now there's something special about that point P. It is the center of all of the circle that goes through all three corners. And I don't know if this is going to allow me to do it, but this is something that we're going to do not in this section, but on 4.5 on Thursday, you're actually going to get a chance to do it. What you're going to be able to do is you're going to be able to take a compass. This is called a bullseye compass. It's called a bullseye compass because it has a kind of a bullseye. You can kind of see these little lines that go through there, and I can put that bullseye on point P. I can put my finger on it, and then I can adjust this slider until it's directly over the vertex C. And if this is right, which I hope I can do this, we'll see if this works. I'm not sure if it will or if it won't. What I can do with this it's slightly sliding, just slightly. I need to scoot this down. Let me see if it'll let me. Oh, it does. What I want you to see is that the circumcenter is the exact center of all 3 points. So what we are learning about with these perpendicular bisectors is, and by the way, when you look at that, doesn't that look satisfying? And you're like, oh, that's so nice. That's how I feel about it. I really do. And now let's think about how this could be used in real life. In real life, let's say you become an architect and you're designing between this ride at a theme park and this ride at a theme park and this ride at the theme park. You probably want to put something right in the middle that's the same distance away from all three. You're probably going to want to put your snack bar right here so that no matter which ride you get off of, you have the smell of kettle corn. That smells so good, I might need to stop by there, right? Or maybe the bathroom. It's equidistant from your three things. It's where you might go pee. I'm not sure if I thought that was funny. Okay. Anyhow. Perpendicular bisector. This circumcenter is created by the perpendicular bisectors, and it doesn't matter if it's acute, a right, or an obtuse triangle. Sometimes that circumcenter is inside or outside the triangle. Like I could look at this obtuse triangle. Let me see if I can do it with this thing. I'm going to put my bullseye right where those 3 points cross. I'm going to adjust, and if I'm going to have to move this and slide it down. No matter where you are, you can get through the edge, all 3 vertices in a triangle, which is kind of nice because I think about doorways all the time sometimes, and I think if I was a carpenter and I really wanted to make that arch just right, how would I know where exactly the center point would be? Well, guess what? There's 3 points. You have a triangle. I bet you mathematically could use this to figure out if I was going to be a carpenter someday where things needed to be, just so you know. The first thing was called a circumcenter. The second thing we're going to learn with this is learn something called the incenter. The incenter is different than the circumcenter because it's created by angle bisectors. Angle bisectors, on the other hand, are equidistant from the sides. We learned that in 4.2. Because it's equidistant from the sides, if I look at this distance and this distance, the side, and this distance, the side, then that means that this and this and this have to be the same. Well, what does that mean? That means that if I have a circle, this circle is actually going to go around the inside of the triangle. Let's see if it works. That just totally moved on me. Let me try that again. Trying to make it work. You see how you can get that circle just inside, touching all 3 sides, because these 3 distances are the same to each of the sides. It's created by something on the angle bisector that makes those perpendiculars congruent to each other. If you look at this one, it's creating distances that are the same. Let me do 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. The distances that are the same going through the vertices because they're on perpendicular bisectors. I hope you see that. These are made from the isosceles triangles we talked about, and then these are made from those perpendiculars to the sides. So with that being said, make sure you know the difference between a circumcenter and incenter, how they're created, because they're going to get confusing. We're going to mix them up on you. Everything else that I have for you is an example in your textbook. If you would like to do these with me in your textbook, you can. We're doing 3 problems, numbers 2, 5, and 22. Number 2. Find the coordinates of the circumcenter of the triangle with vertices -4, 5 for A, for B for -2, 5, and for C, -2, -2. Let's do that. -4, 5 is A. B, -2, 5. For C, -2, -2. Then what I'm going to do is I'm going to connect these. Oh, let's say I'm using a ruler. Well, I'm not. But I am using a straight line tool that helps me. You plot all 3 points. You connect the dots. If you need a ruler, I have rulers for you to use. But it asks you to find the coordinates of the circumcenter. We're going to do this today with just a ruler. We don't need a protractor or anything because this one's pretty simple to do. On Thursday, we will actually learn how to do this with a compass and straight edge. We'll use bullseye compasses and straight edges. If you want to bring your own, you can. Otherwise, you guys get to use what I have a class set of these bullseye compasses that you'll get to use as well if you don't bring your own. So here's what I'm going to do here. I'm going to figure out exactly what is the halfway point between A and B. I know where that is. It's right here. This is the midpoint. Right? I need the perpendicular bisector. I need to go through the midpoint and I need to be at 90 degrees. So I'm going to make a blue line. Let me get this line and I'm going to make it blue. And now I get a line. And I'm going to make sure that it is perpendicular. And since these grids are all perpendicular, let's see if I can grab that and move it over just a little bit. Yeah, that looks better. There is a perpendicular bisector of AB. Because I went through the midpoint and I know it's at a 90 degrees because it follows that grid. It's parallel to the y-axis. That's good. I've done AB. I'm going to do the other side. I'm going to go and figure out what is halfway between B and C. I'm going to count. I'm going to go 1, 2, 3, 4, 5, 6, 7. I need to go halfway. 1, 2, 3 and a half. I'm going to make a dot right about 3 and a half. I needed it to be a perfect right angle there. So what I'm going to do is I'm going to make sure that I am parallel to this line, to the x-axis. And so now what I have is I have this piece which is 3 and a half and this piece which is 3 and a half, and this is a perfect right angle right there. I could do the other side. I can actually measure this if I wanted to. Let's say that it was 6.4 centimeters. Half of 6.4 is 3.2, and I can put a dot at 3.2 right here. And then what I could do is I could make sure that I'm going exactly 90 degrees from there. And I could make a point between here and there, which is exactly 90 degrees from there. And these would be the same as each other. And all three of these intersect at the same point. Guess where that point is? It's right here. Let me go back to red. This point. That's the circumcenter. So all it says is what are the coordinates of the circumcenter. So I know what my x coordinate is. It's -1, -2, -3. My y coordinate goes up 1.5. I'm going to have to use a decimal there. That's the coordinates of my circumcenter. If you want to double check, you could take your compass and you could see if you would go through all 3 points, which doesn't that look like it's going to? Which it does. I'll let you guys do that one later. Number 5. R, when I look at it, can you tell if it's an in-center or a circumcenter? If you know what it is, go ahead and say what you think it is out loud. Those of you who said in-center, you are correct. This is an in-center because an angle bisector, straight here, angle bisector is here. Where the angle bisectors intersect, this is an in-center. It is equidistant, perpendicular to the side. These are the same, which means that RS should be the same as RT, and you can take this 4 parenthesis x minus 3 plus 6 should be equal to the 5 parenthesis 2x minus 6. If you solve that, you could figure out what x is. Distribute Put your like terms together. Subtract 4x from both sides. Add 30 to both sides. I got x is 4. Is that what you guys got? And I always go back and read the question, did they ask me to find x? They did. I do that because sometimes they're going to ask you for RS, sometimes you're going to have to plug it back in, and I need to pay attention to what they're asking. The last question I have picked for you is number 22. '22 is a tough one because it's true or false, but explain why. Determine whether each statement is true or false. If the statement is false, give a counterexample. Only if it's false do we have to give a counterexample. If point C is the circumcenter of triangle PQR and the circumcenter of triangle PQS, then R and S must be the same point. C is going to be the circumcenter of a triangle PQR. You're going to need to think of a triangle PQR. Maybe you'll draw it. And the circumcenter is the point that's going to go through all three, right? And so if there's another point S somewhere around here, is R and S going to have to be the same point if there's a circumcenter, if point C is a circumcenter of this triangle? This one's really hard to visualize. So I came up with my own example down here below. I came up with a triangle with C is the circumcenter of triangle PQR. And I try to think about where would it be if S was not the same point as R, what would that look like? And I came up with this green dot out here. As a matter of fact, the green dot could have been anywhere out here that I wanted it to be. If I had this as S, then what I would have is, let me switch colors. This triangle PQS is it the same center point C? Is that the same circumcenter? Yes. Is R and S, are they the same point? Are they at the same location? If point C is the circumcenter, so as this says, determine whether it's true or false. It is false because of the example that I created down here. I'm going to stop your notes right there.